Hello, this is Jeff at the LTU Print Lab. I'm making this video to demonstrate some of the basic two-axis machining operations available in RhinoCAM 2022. The examples in this video are drawn from our prototyping and fabrication class, but I'm hoping to make the lesson applicable to anybody who's interested in using the CNC in our buildLab space here at Lawrence Technological University. So let me close this window. I've launched Rhino. We're using Rhino 7, and I've opened the RhinoCAM 2020 plugin as well as a file from the prototyping and fabrication class. You see the file with two-axis geometry in the top view on the right, and you see two RhinoCAM panels on the left-hand side. One of the first things that I'm going to do is nest these panels a little bit tighter so that it shows more space on the right, and collapse this just a little bit. 2D or two-axis programming, I should say, starts with two-dimensional geometry, and it specifies a depth of a cut. So the CNC router will follow a shape or a line, cutting material either to the inside, to the outside of that line or shape, or along its path, depending on the machining operation. The two operations that we're going to look at today are profiling and pocketing, and we're also going to talk about defining some machine properties, properties of the stock box, and order of operations and why they're important. So to begin with, I'm going to look at the program tab within the RhinoCAM window here. Let's peek inside the post option here just by double clicking. We have a shop bot, and I've selected that already from a list of available makes and models of CNC routers. We have a shop bot, so I have that selected, and I'm going to confirm by saying OK. Now, I mentioned units. This model, this design was drawn in inches, and if we need to check those, we can go to properties and look at units and see that the units for the workspace are in inches. This is important because the machine is expecting the values to be defined in inches. All right, so moving down, we have our stock box. This is going to be defining the actual kind of dimensions of the material we are using. So we have this defined already, but I'll show you a little bit more. We have a 48 by 48 inch box in the top view here, defining the dimensions of a piece of plywood. And within that space, we have the geometry that we are intending to cut today. So if I double click on the stock box, you'll see a representation of the corner coordinates. The way we set it up in our shop is we set the corner coordinates for the origin at 0, 0, 0, and the dimensions as that of the material, so 48, 48, and 1/2 inch. As the dimensions of the material, and we use our point of reference as the top southwest corner, and you can see that indicated here. We're doing it this way because it allows users who are designing work to position their geometry relative to the world coordinate system and the origin. And anytime we're defining values in the software which have a depth, we're going to be cutting into the negative Z dimension. And remember, we set that tolerance for the machine, the maximum depth at 0.05 here specified in the material. So that will ensure that we're not going to cut into our table. There are various ways we could set this up. We're just using this as an example today, and how we will often do it in our shop. So I'm going to confirm these choices by selecting OK. We could, if we would like, define fixtures that would be anchors of some kind by first drawing them as geometry and then selecting them. So if you were to double click on this, you would be allowed to then select that geometry and define that as a fixture, which will be will be avoided by the machine operations. And the last one in this menu is the setup, and we'll come back to this. This is where we will be defining the operations in sequence. Before we begin, though, we also need to define some tools. Today we're going to define our own tool by double-clicking on the tool in the machining objects menu here, and I'm going to define a flat mill today. So I'm going to select flat mill, and I'm going to define some attributes here below. So the shank diameter for this is 1/4 of an inch, the overall length of the tool. And if you look at the illustration here, that's measured from the bottom of the collet to the tip of the tool. So in this case, the total tool length from the bottom of the tool to where it fits in the collet is going to be 3 inches. However, the collet is 0.75 inches from top to bottom. So the overall tool length is going to be 2.25 measured from the tip to the base of the collet. For this one, the shoulder length, which measures from the top or from the bottom of the tool tip past the flute length or the cutting edges to where chips can be discarded, that goes up to 1.75 inches. The flute length is 1.5, and the tool diameter is also 0.25. And you should see an updated preview of what that looks like right here. This tool has 2 flutes, and we're going to leave some other defaults here, the tool number as 1. We do not have a tool changer on our current machine, so we're just going to ignore that for now and keep it simple. We're going to save this as a new tool, and I'm going to give it the name flat mill 1/4 inch, and save as new tool. You see it here on the left. And then I will exit, and if I open up that menu, you can see it here on the bottom. So I'll close that. And I'm going to kind of shrink this machining object menu so that I can move on to a machining operation. All right, so first thing in terms of defining a machine operation is I'm going to define the work 0. This will be the reference point from which the machining operations are measuring their G-code values. So let me just quick switch to the perspective view so that we can kind of rotate this around. You remember our definition of the stock box. We have 1/2 inch in the negative Z dimension, and we have all of our geometry located right here on the XY plane. And just to make sure that everything is in good order, we can actually select all of that and use the Rhino command, project to C plane, and we'll delete input objects, yes. And that will just ensure that all of the objects are at the proper Z height, because the depths which are calculated in the CNC operations will be measured from the geometry in the file. And it's very easy to be just a little bit off and have that cause problems when cutting. So we just want to double check that, and then I'm going to return to the top view here. I'm going to click on Machining Operations in the Program tab, and I'm going to select Work 0. We are going to set the Work 0 to the stock box. We are going to use the southwest corner, and this, as you can see, matches the stock box that we defined earlier. So stock box, highest Z, southwest corner, and we're going to click Generate, and that will create our first operation. Nothing really happens in terms of machine movement during that operation, but it's the starting point. All right, now that we have the Work 0 defined, we're going to start our first machining operation. So I'm going to go to the 2-axis menu, and I'm going to start with pocketing. So pocketing will remove material within a selected geometric boundary. This could be used for making kind of areas to fit tabs together, or make a topographical surface. Just follow along, I suppose. All right, our control geometry, in this case, we're going to select curve edge regions, and I'm just going to select this one rectangle, which we're going to recess below the surface by a value of 1/8 of an inch. So I'm going to select that and hit enter. That now appears as drive region 1. We're going to move on to tools and select the flat mill that we defined just a few moments ago. We're going to go to feeds and speeds. Now we could have, in the definition of the tool, entered some values here, but I'm going to enter them manually today. We're going to use a spindle speed of 10,000 rotations per minute. We're going to use a plunge of 100, approach of 100, a cut of 200, and a retract of 200. And departure of 200. And these are simplified values, but as a general recommendation, the plunge speed should be half the recommended cut speed, which is referred to as the feed rate. And the feed rate together with the spindle speed, the diameter of the bit, and the number of flutes all kind of come together in an equation called calculation of chip load, which we're not going to go into in this video, but that's the origin of these values. For transfer, that is motion between geometry, we're going to use the rapid option, which is the highest travel speed for the machine, even though in this operation there is only one piece of geometry. Next, we're going to define the clearance plane as the maximum Z value of the stock plus a value of 1. So as you can see in this illustration, it will lift 1 inch above the stock material when it's traveling between objects in the machining operation. And we'll see that that'll make more sense in the next one where it's traveling between these different geometric components. Again, this just has the one single component in this operation. Under sorting, we're going to select minimum distance sort, and that will just prioritize the sequence of objects that are cut. Under advanced cut parameters, we're going to uncheck perform arc fitting. This is a recommendation that our lab has come to after experiencing occasional errors in the G code that's produced. We don't know the reason for that, but it does relate to performing arc fitting, so we're going to turn that off. In the menu for pocketing, entry, and exit, we're going to define an approach motion that follows the length of the path, and we'll go ahead and use the pre-specified angle and height for that approach. And then likewise, when we're retracting, we are going to retract in a linear motion as well. Under cut levels, this is very important. We're going to select at top for the geometry. So again, our geometry is located at the Z value of 0, and we're going to be cutting downward into the material. The total cut depth for this operation will be 1.25 or 1/8 of an inch. And with the bit size of 1/4 of an inch, we can cut that full depth in a single pass. So we're going to do that all at once. And lastly, under cut parameters, we're just going to take a look at this. I don't know that we're going to be making any changes. You can see the global tolerance, that is the maximum distance between the tool path and the geometry, is specified as 1/100th of an inch. If you would like a smaller tolerance, you can select a smaller tolerance by adding a 0, but the tolerance cannot be 0. In this case, it will the program will not let you do that. Down at the bottom, the step over distance, that is something we're going to change today. The step over distance is defined as a percentage of the diameter of the tool bit. The default value here is 25%, which means that it moves over 25% of the width of the diameter of the bit with each back and forth stroke. We're going to up that to 50% for this one because it's a fairly shallow cut, and that will speed things up just a little bit. You can also change the geometry, the way that it kind of spirals around the space in a linear way or a radial way. But we're just going to leave it as the offset. And for this operation, we're going to be using a down cut bit. So we're going to select climb, which will define the operation in a counterclockwise way, as opposed to a clockwise way for an upcut bit. Lastly, we're going to click generate, and that will generate the tool path, which you now see highlighted in cyan on this setup here. And if we move to the one of the other views, for example, the front view, you can see that the depth is below 0 in the Z dimension, and you can see the approach move and then the cutting depth. One thing that you'll notice though, and I'm noticing right now, is that initial approach, we should check the value there, because as it engages the material, first it comes down in a straight vertical way and then an angle. We actually want that angle to start a little bit further out so that the bit will be entering the plywood at an angle. So we're going to double click on that pocketing operation to go back in and make a change here. We're going to go to the entry and exit. Oh, I misread the height. I thought it was from a height of 0.05 rather than, or 0.5 rather than 0.05. So let's say starting from a height of just above, we'll go 0.6, and then we'll click generate. And you can see now that it is entering at an angle. It's actually kind of spiraling in. If we go to the perspective view and zoom in, you can see that it enters with a spiral motion that follows that first path. All right, that works for me. We can preview that by right-clicking on the operation and then on simulate, and you can watch a representation of the bit as it performs the operation, and you can see it cutting into the stock material here, and you can see the distance between the geometry as it was defined here, the tolerance value that was specified in our setup, and you can see also the radius that on the corner, because as the bit travels through the material, the bit itself is round, and so it's going to leave a little radius on the corner here, which is equal to the radius of the bit. So that'll be a 1/8 inch radius in that corner right there. We're going to go ahead and leave that as it is for now, and we're going to define the next operation below. So here you can see in the setup that the sequence will start with a work 0 followed by a pocketing operation. And now we're going to define another operation, which is also found under the 2-axis menu, called profiling. For this, we're going to be cutting out the shapes that we saw on the setup. And so I will select curve edge regions. I'll kind of zoom back, and I will select these other ones here as curve edge regions. I'm going to, let me see, can I unselect this one? I'll have to do that in a minute. So the original geometry that we had selected for the pocketing is still selected here, so we're going to need to unselect that in just a minute. I'm going to go ahead and click enter. You see these drive regions. I'm going to go to drive region 1, which we defined earlier, and I'm going to remove active, so that will take that out. Now we're only going to be doing the profiling operation on these others. Many things will be the same for this. The tool, for example, will be the same. The feeds and speeds will be the same. We'll just enter those here. So 10,000 RPMs, 100, 100, 200, 200, and 200. All right. Our clearance plane will likewise be the same. Our cut parameters, our global tolerance here, as it was defined previously, will be the same. You'll see that some of the menu options are a little bit different for this. We're also going to select the step down or climb for cut direction. We'll be using the same bit. The start point for each of these will be defined here. That is the start point for each of the individual part regions is initially selected as the midpoint of the longest side, and we'll see how that turns out when we come to selecting tabs and bridges a little bit later on, but we'll leave that as it is. The cutting side, we are going to use the option use inside or outside inside for closed curves. and we're going to select outside because we're going to cut around each of these. If you wanted to cut out a window, you could select inside and that would cut within the selected areas. Today we're going to select outside. And for this, there will be no step over. We're just going to make a single linear path that goes around the part. All right. For sorting, we're also going to go to minimum distance sort, and it will follow some kind of orientation roughly approximated here, where each of these corners represent one of the geometric objects. It's not terribly important in this example, you know, that we start in a particular area. The piece will be clamped down, and so it's not going to be an issue. We'll go to cornering parameters, and we're going to talk about one other option here, which is called the dog bone. And that is because we're making a friction fit box in this example, where the tab of one piece is designed to fit within the space of another. And as we saw the radius on our pocketing operation, that would interfere from the tabs fitting together properly. So we're going to select dog bone, and what that will do is it will notch out a little bit of extra material at the corner, such that the rectangle looks a little bit like a dog bone, if you will. And we'll look at that again in a moment. Moving on to the advanced cut parameters. Again, we're going to turn off arc fitting. And at the bottom here, when we're looking at tabs and bridges, we're going to add rectangular tabs, which will keep the parts connected to the larger piece of plywood while cutting, so that they're not breaking free. Usually you want to have somewhere in the range of, you know, maybe 2 to 4 tabs for small pieces, and maybe 8 or more tabs for very large pieces, depending on the complexity of the geometry. It'll be a kind of a case-by-case basis. I'm going to look at using 4 tabs for all of these, and I may make some changes based on their automatic placement, as we'll see in a moment. We're going to define the bridge height a little bit larger than we might otherwise. We're going to make this a 0.25 bridge height and a 0.25 bridge width. What I recommend is a bridge height that goes at least through 1, maybe 1.5 of the internal plies of a piece of plywood. So I know that this plywood has 3 internal plies, and so I'm going to make those bridges a little bit taller so that they're a little bit less brittle. And I'm going to select 4 for the number of bridges, and move on to entry and exit. For the entry, we're going to select a long path in the same way that we did with pocketing. This will make the router bit enter the material at an angle. Very similar as before. I'm going to select a slightly higher angle, again, of 0.6 as the height, not angle. I'm going to change the height of the approach to 0.6 and a long path at 10 degrees. And as far as an exiting curve, we're going to just say none. It'll come up out of the material directly when it's finished. The cut levels will be defined at the top again, the geometry at z equals 0. The total cut depth will be the thickness of our material, which is 0.5. In all truth, our material is 0.48, which means we may cut 0.02 into the spoil board. However, we find that this is appropriate if the material is warped, which it frankly often is, a little bit warped, and we find that a 0.02 cut into the spoil board is acceptable in many cases. So our total cut depth will be 1/2 of an inch. We are going to specify the rough cut depth at 0.5. We're just going to make this all kind of rough cut. The differentiation between rough and finished depth just allows you to assign slightly different parameters to the upper and lower regions of a CNC pass here. We're just going to call it all rough cut, and we're going to say that each one of those rough cut passes has a depth of 0.25. Again, a good general rule is that the maximum depth should be equal to the diameter of the bit. So here we have a 1/4 inch bit and a 1/4 inch rough cut depth, which means it will take 2 passes around each one of the geometries to cut all the way through, and that will complete the job about as efficiently as we can. I'm going to click generate at the bottom to generate that toolpath. And if you zoom in here, you can see the two paths tracing around the outside of each one of those geometries. And you can see at times, as in this corner here, where the bit will lift up and allow for a tab. So here is a tab located kind of in the middle of that side. That's a good location for a tab. Here, this tab is located in the corner, which is not ideal. So we'll look for other instances of that as we kind of scan across the geometry. Looks like these larger objects here, these two, the tab placement is pretty convenient. It's located right in the middle of some of the sides, but for the smaller geometry, the tab placement is sometimes kind of awkward, as it is here at this corner. And we may wish to fix that up in just a minute, but we're going to move on and look at a preview first. So from the overhead view, if I switch to top, you can see in red the travel motions where the machine will lift up to the height of the clearance plane while it moves between each of the different geometries. And you can see the path that it follows through. It will start here in the lower left, then it will do this one, move down to this one, move up, and kind of sequentially through the set. Let's take a look at the preview for this. We're going to start by clicking on the setup. We're actually going to do a simulation of the whole setup. So you can see first, there we go, the pocketing operation on this, which is listed here because the simulation is for the whole setup. And then you can see each one of the individual objects getting cut out. And if I zoom in, I can see the placement of the tabs, and you can see how the bit angles toward the corners, clearing just enough material so that you can fit one tab into another. This in reality would be rounded, but in the simulation, it's got a little bit more of a geometric look. That's just kind of saving on memory as the computer simulates it. Here's an instance where the tab was created near a corner, and it pretty much cuts itself off because it's measured from here, kind of in, out, and anyway, so the tab isn't going to work on that one. And I suspect that the same will be true on many of the others here. The smaller pieces. Yeah, in the end, that tab is not going to work. This tab is not going to work. And so in the end, only two tabs would be there, and one of them is on a corner. So that's not very convenient, and we're going to want to fix that. But this is a good place to start. So in order to define new tabs for the other operation, we're going to define a new operation. So I'm going to right click, and we are going to clone. So now we have two identical operations. I'm going to go into the first one, and I'm going to remove some of those geometries. So I'm going to select drive region 1, and I'm going to remove active. I'm going to get rid of all the smaller ones. Remove active, and remove active. Okay. I'm going to click generate. And so now this machining operation just has the two larger geometries, and those look pretty good. I'm going to go ahead and name this one 2-axis profiling. I'm going to say LG for large. And then I'm going to click on this machining operation. I'm going to go in there. I'm going to find those larger part regions. This one, remove active. And this one, remove active. And we're going to make some changes to this. Now we'll try, let's see, we're going to go to cut parameters, and the first thing I'm going to try is unchecking the start point. So again, as I mentioned earlier, the midpoint of the longest side is the default start point. I'm going to uncheck that and click generate and kind of see now where the tabs land. I'll double click on this to name this one SM for small. So I've got three operations: pocketing, profiling of the larger pieces, and profiling of the smaller pieces. And let's then click on the setup and simulate. You'll see the operations performed in sequence. And I'll zoom in on these smaller objects, and you can see that now we've got 3 tabs. It's still cutting one off over here. That's kind of a bummer. It's nice that they're added automatically, but in some cases, the situation is not completely ideal either. The next thing I'm going to try in order to make it better is I'm going to, again, go to the advanced cut parameters, and I'm going to change the number of bridges. I'm just going to add 1 to 5 and then click generate and simulate again. Here we go. Here we go. Fingers crossed. 1, 2, 3, 4, 5. Okay, so in this case, we still have tabs on 2 of the corners, but they are all there. None of them are getting cut off. They're pretty well balanced around the perimeter. And so I would say this is acceptable. You can see that this one gets a little bit small as the bridge size is measured just prior to the bit either entering or exiting that corner. But it does look substantial enough that it will stay in place. And so I think that that's probably an acceptable solution here. All right, so that about does it. I'm going to change from the top to the perspective view and kind of carefully look at the underside, make sure that none of the cyan colored tool paths are extending below the stock material. You could do this in the front or the side view as well, and just kind of see nothing too bad is happening. Here are those approach motions, you know, kind of following along the edges. Probably more obvious again in the perspective view. If I come up in here. Looks a little funny because as it follows the path, it's kind of following it around this zigzaggy corner. Maybe that's higher than necessary. Let's maybe change that. We're gonna go to entry and exit. Let's go to 0.1. I think it's measuring from the top of the path. Let's click generate. No, that feels like it's starting below as well. Yeah, that entry motion is below. No, I'm just kind of guessing, I have to admit. Oh, okay, so I entered 0.25, and so it's going to the surface, so it's 0.25 measured from the depth of the cut. So we're cutting to a depth of 0.25, so if we start at 0.25, it'll come to the surface and then enter that way. So let's mimic that in the other one for the large objects. Entry and exit. Rather than that, we'll select 0.25 and generate. Kind of zoom out, we'll see that here where it kind of comes just into contact with the face and then enters at an angle and then proceeds to follow the path counterclockwise. All right, I'm feeling pretty good about this one. We'll return to the top view. One last thing before we go. If you click on the setup, you'll see all of the things you can show and hide. The stock box, tool paths. These are some buttons along the bottom here that will show and hide some of the various preview tools. You can also make some changes to the simulation, speeding it up or slowing it down if you wish. A last thing that I'm going to check before I export this is I'm going to select the setup. I'm going to right click on that and I'm going to go to information, and this will show in sequence each of the operations I have defined and the amount of time they're projected to take with a cut feed as specified here. And you can see that this will take, it is projected just shy of 10 minutes to complete the 3 machining operations as we set it up today. That sounds pretty reasonable to me. I'm going to say OK. And the final step, we need to produce the G code for this file. So again, we're going to right click on the setup. This time we're going to select post. It will pull up the menu for saving files. I'm going to name this one demo, and I'm going to select the format here. SBP is one of the preferred types. .NC also works. There are a couple other options that the machine will recognize. I'm going to leave it as SBP for now. And I'm just going to save this, let's say, to my downloads. I'm going to throw it in there. There it is, downloads. I'll just drop it in and click post. So it'll pop up a window on the screen, and it will show you the actual G code that will be used to drive the machine. And what you see here are each one of the target points, as it's going to an XY coordinate and a specified depth. So here with a decimal value like that, I'm actually kind of guessing that it's maybe an approach motion to a specified point. Yep, so this is probably an approach motion coming to this specified depth of 1/8 of an inch. And then it will move at this speed, kind of around that geometry. This must be the pocketing operation at the beginning. And you can see some of the other ones here. This will be one of the profiling operations at a negative 0.05. That will be one of the profiling operations. Anyway, thanks for watching. This is the basic setup for doing 2-axis operations, profiling, and pocketing. If you have any questions, please stop by the buildLab desk. Talk to one of our staff members either up here or down in our buildLab, and we're happy to help you out. All right, thanks.